All right, welcome everyone to my presentation on the minimum bottleneck spanning arborescence problem. That sounds complicated, but hopefully, but after our introduction here, everything should be pretty simple to understand because it's fundamentally a pretty simple problem, at least to state. So, I guess since everyone here is somewhat familiar with graphs, I'll just, give a brief revision. So, a graph is basically just a collection of vertices, so these nodes here, and edges. The edges can either be undirected, as in there's a symmetric in terms of, if we have this edge here, then I can reach this vertex from this one, and I can also go the other direction, right? Um, whereas there's also another type of graphs called directed graphs where the edges have a direction to them. And so this, for instance, this edge here, I can only go from this vertex into this one. Like I can't go the other direction. Right. Does that make sense so far?
Yep.
All
Yeah.
right. Okay. So now, a common sort of structure that you would want to extract out of a graph is often called a spanning tree. So let's just sort of break that down. So what is a tree? A tree is essentially just an acyclic graph, if you want to think about it that way. So what
An
is a
acyclic
cycle?
connected graph.
Yeah, a connected graph that has no cycles, I guess is the uh, full way to describe that. So what is a cycle? I guess, I mean, our graphs are already connected, and connected just means you can reach every vertex from every other one. Although in directed graphs, an equivalent notion would have to be strongly connected because due to the asymmetry of the edges, because potentially you can reach like I said, like let's say this one from this one, but not the other way around, right? All right, so so in order, okay, what is a cycle, right? So a cycle is essentially a set of edges where you can reach your starting vertex from itself. So, like if I go through this cycle here, I can end up back where I started. And similarly here. And that is something we don't want in our final tree structure. And so let's say I want a tree, I have to get rid of that cycle and let's say get rid of that edge. And this is a tree. Why? Because there's no cycle left. Hopefully that should be pretty clear. And all of the vertices are connected to each other. Right. So yeah, I can reach everything. And what is a spanning component of the tree? Spanning essentially just means, as I said, it reaches every vertex. Like if I were to say get rid of this edge here, now I have two trees, which is often called a forest. But it's no longer, each tree is no longer spanning, right? It only reaches a subset of the vertices. Okay. So that's the spanning tree structure. Um, like I said, there's sort of an asymmetry when we try to move this over to directed graphs. And so what the equivalent notion to a spanning tree for directed graphs is something called the spanning arborescence. And essentially there, um, how we deal with the asymmetry of the edges is essentially to designate a root vertex and then sort of define the edges as either always going out from the root. So let's say this thing here is the root. So all of our edges have to go away from the root, or all of edge, or inversely, all of our edges have to go into the root. And these are called, respectively, out trees and in trees. To sort of describe whether the edges are going away from or into the root. Okay, let's see. So now that we've sort of described our spanning tree and spanning arborescence that we will need to do our graph algorithm to find. What is some more common optimization problems that we would like to do on our graphs? Well, the most common objective is, let's suppose our graph has some weight here. So let's see, maybe this is 1, 2, 3, 4, 5, 6, 7. Okay. So let's say, there's a cost associated with traveling an edge. So let's say, you can imagine this as like a road network or like a power line, and so like sending like a vehicle through this one takes 3 hours, and to this road here takes 2 hours, right? And ideally, you if you're designing like a road network, you would like the sum total of all of the roads to be as fast as possible with as few roads as possible, and still be able to reach, let's say every town on the map. So that's one like practical abstraction for a graph. Anyway, so so that's so essentially I guess like we can try to brute force our way here to show an example. So let's see. Well, we would like to keep these low weight edges, so maybe get rid of the 7. Let's see, and the 6. Yeah, I think that's can we get rid of anything else?
That looks
I don't
optimal to
think.
me.
Yep. So yeah, we've just created a minimum spanning tree. There is what it's called, and I guess more accurately, it would be called the minimum sum spanning tree, because we're trying to minimize the sum of all of the weights of the edges. And yeah, and so an equivalent notion for this minimum sum spanning tree for directed graphs is called a pretty straightforward, self-explanatory, a minimum sum spanning arborescence. And the algorithm for it is a little more involved, but essentially, you designate a root vertex, and then, all of the edges will have its own weight, and you try to find the one that the spanning arborescence that adds up to the minimum amount of weight. So that's the sum objectives.
And are
Like
we
I
And
said,
just as a
checking for...
reminder, you're orienting it so that all of the other vertices are reachable from the root, right? Like it's directed out.
yeah. So like, let's say like these two, let's say like these two edges here are like really expensive. Like your algorithm ideally should not like delete both of them, because then you can't form a tree or an arborescence in this case anymore, or is there spanning one? Does that make sense? You need to still be able to reach every vertex. Is everyone with me on that?
I'm with you.
Yeah.
Okay. All right.
So just to check my understanding here, we could get rid of this one, and then call this one the like root, and then we're good. Oh, and sorry, we also need to get rid of this edge.
Yes. Let's see here.
And that would be an out tree. And if we're trying to do an in tree...
Oh, actually, you can't get rid of these ones because you can't reach this one here.
Oh, sorry. Yes, you're right. So you keep... Oh, sorry, yeah, you get rid of this one.
Yeah.
Okay.
That you can do. You can go over here, assuming like this edge has a smaller weight than this one, and so
sure,
it adds up to
yeah.
So we can imagine that black vertex, for instance, is like a factory, and you're trying to pave the fewest miles of road so that you can reach all of your customers or something like that.
Yep.
Yeah, essentially.
Sounds right.
And road design is one of the like main application of graphs. The other one is social networks, but
And are we only considered with the outgraph problem?
yes. So you can imagine like any algorithm you can run to find an out tree, you can run to find an in tree. You just have to
Flip the edges
reverse the
first?
edges you're considering, right?
I see, yeah. That makes sense.
Yeah. And there's also another duality, but we will get to that quickly. So yeah, so essentially that's the minimum sum objective. You're trying to minimize the sum of all the weights. But while these objectives are like, the predominant ones, like, the minimum spanning tree problem is probably like something like every undergrad in CS will have to learn. It's like one of the most popular optimization problems. It's so the minimum, even though that's the case, the minimum sum is not the only metric by which you can sort of measure the quality of your output spanning tree and spanning arborescence. Another objective is the bottleneck objective, where you are trying to minimize the maximum weight. And in like optimization literature, I guess, this is also often called the the minimax objective. If anyone's into like sort of game tree, that's the same minimax as this one. And equivalently, you can also define a maximin objective, even if you wanted to minimize the max, via just like inverting the edge weights. So like make everything negative, and then your maximin becomes minimax after you've inverted it again at the end. But we won't go over that too much. Just I say that for everyone to be aware that there's nothing special about the minimax. Particularly, you can equivalently define a maximin problem.
For the minimax problem, it seems to me like you can approximate it using the minimum sum problem by replacing every weight W with 10 to the W. Like if you imagine all of those weights that you have in the top graph, you replace them with 1,000, 100, a million, etc., then it would be pretty much equivalent to trying to just minimize the maximum one that you have, I think.
Okay,
Actually, yeah, I believe if you find this minimum sum, that automatically becomes the minimum bottleneck spanning tree, I believe.
Good. That's I'm just about to get to that. Everyone has the right intuition, but there's a special thing. So for undirected graphs, there are two properties that we need to be aware of. So let me move over here. So there's two property for the undirected case. So there's a cut property. So essentially, let's say these are this is two subgraphs, and then there is some number of edges connecting between them. So the cut property states that this is a subgraph, this is a subgraph, and they all add up to the original graph, and between them there are some edges. So what the cut property says is that for a minimum spanning tree, the edge weight between every cut has to be minimum. So let's say like they have weights like 1, 2, and 3. And so so the cut property says the weight between these has to be the one edge. It can never be the 3 edge. And so this has to be the minimum weight across the cut. And so that's called the cut property of the minimum spanning tree. And because of this property, a minimum spanning tree in an undirected graph is always necessarily a minimum bottleneck spanning tree as well. However, the inverse direction is not true. So a minimum bottleneck spanning tree is not necessarily a minimum spanning tree. All right, is everyone with me on that?
I think so, but does that not I don't think that invalidates what Akiva said, right? About the like 10 to the X thing. Like you would just, it's not necessarily a minimum spanning tree for the same graph. It's just a minimum bottleneck spanning tree for a graph with the same shape but different weights, right?
Yeah. So I guess like what you're trying to say is like, you're trying to like reduce our graph to like some other graph and then solve that problem instead.
Yeah, I think the I mean, I don't know if you're I'm not sure what your stance is. I'm not sure if you're saying that's not the case, but like it seems to me like you can just pick some base, then raise each of these numbers to that base, and then under like if the base is high enough, then the minimum spanning tree problem becomes the minimum bottleneck spanning tree problem.
Oh, okay. That could be the case. I haven't really thought too much about that direction. Although, like I said, like because of this property, like every minimum spanning tree is already guaranteed to be the minimum bottleneck one in our undirected graph. And so,
Okay, gotcha. Oh, it is guaranteed to.
yeah.
I see.
So,
I see.
okay. So I guess let's to make it more clear. Minimum spanning tree. So minimum sum implies minimum bottleneck, but minimum bottleneck does not imply minimum sum in our undirected case. Okay. Right.
Wait, so
So
there are some
because of
cases where there are two minimum sums. It sounds like for that to be the case, you would have to be able to create two minimum sums, but they're
oh,
not.
yeah, okay. I guess I should have stated that as well. A minimum sum spanning tree is not guaranteed to be unique.
Right. And the fact that you just stated depends on that, right? If I'm
Yeah.
following you. Okay.
Okay. So none of these spanning trees are guaranteed to be unique. In fact, there are algorithms that not only find the spanning trees, but also like iteratively list them with the changes between each tree. Although that's slightly more involved. Okay. So, like I said, so a minimum sum implies a minimum bottleneck for our undirected case. However, so like every minimum sum algorithm can also solve our minimum bottleneck problem in the undirected graph. Um, and the minimum sum problems for the undirected graphs are already pretty efficient. So the minimum bottleneck objective in the undirected case is a bit less motivated, you could say. Um, Someone drawing something?
Yeah, sorry. I was drawing what I think might be a counterexample to what you just said. Um, Either that
So
or
you're saying like
like
so you're saying like
I,
minimum sum tree that's not minimum bottleneck?
I might not have drawn this correctly, but minimum sum tree that's not minimum bottleneck. Yeah. Yeah. Maybe I didn't. Maybe this doesn't work. I was hoping that you would either be forced to delete the 5 and the 3 or the 4 and the 4. We can always just delete the 5 and the like a 5 and a 4.
Yeah, no, it's like I mean, yeah, I haven't even gotten to like my results yet, so it's usually this is like, been pretty well established. So if you found a counterexample, that would be pretty huge news.
But why would minimum bottleneck not imply minimum sum?
um because okay, you can imagine that you need to like it's possible that because okay, I guess essentially a minimum bottleneck is an easier problem. So I guess to go more towards preliminary theory here, uh, the minimum bottleneck is some weight, right? So it has a bottleneck weight that it's called. So here in our case, the bottleneck weight is the 6 here. And so once we found our bottleneck weight, any spanning tree with weights under or any less than or equal to this is a minimum bottleneck spanning tree. Whereas the minimum sum is a bit more involved. You actually need to calculate the sum to guarantee that, right? Or like, explore some structure in order to guarantee the minimum sum. Whereas for the minimum bottleneck, as you have to include the bottleneck. And once you found the bottleneck, you can just include only edges that are less than or equal to the bottleneck, and that makes it easier in some sense. So like, let me see here. So like, instead of the 7 here, let's say there are 2 edges. Like, oh, my bad. So let's say like there's one that's like 5 and one that's 4. So once you found the 6th edge here and this is the bottleneck, it doesn't really matter if you include a 4 or a 5. Either of those spanning trees with either edge would be a minimum bottleneck one, because the bottleneck is 6. Whereas, the minimum sum, you might need to include something else.
So minimum sum implies minimum bottleneck and not the other way around.
Yes.
Okay.
Yeah. Yes.
Yeah.
In the undirected case.
Gotcha.
So here's the next part. In our directed graph, this property doesn't hold. Very fine. And so here's a sort of a minimal counterexample. So let me see here. Okay, that's a little big. Okay. All right. So we have this edge here. Let's see. And this edge here. And this edge here. And this edge here. Right. So that's let me think. That's 4, 1, 3, 3. All right. So, can everyone see the graph at the bottom here?
Yep.
All right. So, for our directed case, this property of the min cut property doesn't quite hold anymore. So here, for a minimum bottleneck one would take these at 3 edges, right, to avoid the 4 here. And so the bottleneck in this case would be 3, but the sum between these two would be 6. However, the minimum sum one would take the 4 edge and then the 1 edge, because 4 plus 1 is 5, which is less than 6, right? However, that would increase the bottleneck to 4. So hopefully this minimal example should demonstrate independence between like minimum sum and minimum bottleneck for the directed case. And therefore, you can't use algorithms for minimum sum for minimum bottleneck in the directed case.
That makes sense.
All right. All right. And so now that we've sort of established the problem, does anyone still have questions about our goal here, like what our algorithms are trying to find?
Well, I'm curious what the current state-of-the-art best algorithm is here.
All right. Hopefully that should make sense to everyone. And so let's dive into some algorithms. So now that we've like established the goal for what we're trying to find. So the first algorithm, called Camerini's algorithm, was first developed for the undirected case, but it works reasonably well for the directed case as well, with some logarithmic slowdown. Essentially, what you can do is you can list out all of the edges in like an unsorted list, and then you can iteratively find the median, and then test whether like the lower half of the weights form a spanning tree. If it does, then that means you've overshot, and then you find the median over here. If this does not form a spanning tree, then you recurse on the other side and you find the median over here. And essentially what this allows you to do is to do like a binary search over the edge weights in order to find the bottleneck weight here. Does that make sense? So maybe an example of running the algorithm on our graph might help.
I think I follow, but the bottleneck is just defined as the maximum. Like, what is the definition of the bottleneck? Just the biggest node or the biggest edge that is removable, or the biggest
That
edge
is
that
is
is
unremovable, as in you need it in your graph essentially.
Oh, I thought you said 6 was the bottleneck earlier, but we did remove that edge, didn't we?
Oh
Oh
yeah, my
yeah,
bad.
in that example, it was 5 actually. Yeah, it had to be
Yeah,
5.
my bad.
Okay.
Yeah, but let's say this is. Yeah. Okay. And then I don't know. Let's say this is something else. So I don't know. Let's say this is I don't know, 8. Okay. So let's see here. So let's do like a bougie median finding here. I think that the median should be like 5 or something. 1, 2, 3, 4. Actually, yeah, it's either 4 or 5. Either is well defined. Let's say 4. So let's say, can you form a spanning tree if only 1, 2, 3, 4? You can't because of these guys over here. So you recurse on the bigger half and then you try again. So let's see. So now you can form a spanning tree with these two added and this. So until you've narrowed it down to not include the 8, but include the 6. And now that you found the 6, you're done pretty much. Any spanning tree with the remaining edges less than or equal to 6 is guaranteed to be a minimum bottleneck 1. Doesn't really matter whether you include this, or or even this, because the bottleneck stays the same, right? Even though the sum of their weights are changing.
Yep, that all makes sense.
Okay. And so now that the correctness of the algorithm is sort of demonstrated, the only left is to figure out how do we optimize this running time, right? And so what Camerini does is something called an edge contraction. Basically, let's see here. You have 2 edges that are connected to each other. So, and then, oh shit. And then essentially, what an edge contraction does, let's say you have this edge connecting them here, then they each have some edges connecting them elsewhere. So, and then what an edge contraction does is you're basically merging the 2 vertices together into one super vertex that has all of the edges of the 2 vertices is merging together, and then you delete you forget about the middle edge here.
This can give us multiple edges in loops, right?
Yeah. And so if this
By multiple
introduces,
edges, I mean parallel edges, pairs of edges with the same endpoints.
yes. And then if you have any self loops introduced by this process, it should be easy enough to get rid of them. Parallel edges don't affect us too much, because the amount of edges can never grow more than the original number of edges in the original graph. Okay, I'm assuming that makes sense to everyone. And so what edge contraction allows us to do is to essentially geometrically reduce the number of edges and vertex after every recursion. So when we're recursing into the bigger half here, we can sort of contract everything in the lower half into one super vertex, because we know these edges here don't affect the bottleneck, right? So we can just contract everything. So let's say when we recurse on the medium of 4 here, we knew that everything less than or equal to 4 will be safely contracted. We can just squeeze everything here into one super vertex, and then that would leave us only 3 edges to consider instead of the original however many here, like 8. So like, you can imagine like after having decided that the 4 edges here are insufficient for a spanning tree, you can just contract everything into one big ones, and then you're only dealing with this edge, this edge, and this edge.
And the goal there is that now whenever we do like attempt to cut everything out up to some hypothetical like hypothesis bottleneck, then we have to do less actions to be able to check if that's a valid tree afterwards.
Yeah, so fewer edges, fewer vertices, and if you work it out, then like at each step you're reducing it by at least half, and so that gives you like a geometric
series.
Yeah, geometric series. Yeah,
cool.
Calculus hits back anyway. and so yeah, essentially you start with like E edges in the start, and so after one recursion, it's half of the edges, right? So E over 2, E over 4, and so forth, and that sums up to just 2E, which is still linear time in E.
So this comes out to O of log n plus n, which is just the same as just O of n itself.
Yeah, essentially.
Cool.
Okay. So that's for the undirected case. For the directed case,
and wait, sorry. So just to make sure I'm adding all this up, the best algorithm for like normal minimum spanning tree is like prims and kruskals, right? If memory serves.
So those are the classical algorithms, and they're pretty good in practice. So you would always want to use them. But
okay.
the actual fastest one is uses something called a soft heap, which is like a heap with some amount of small error allowed. And what you get there is like, E times like the inverse Ackermann of E. So I won't go too deep into that, but since
okay. And prims and kruskals are what? N log n or E log E rather?
Yeah. Okay. So for is E log E, but for a connected graph, that's E log V. You can reduce that. And then for prims, it's just essentially modified Dijkstra's, which is E plus V log V, assuming you use like the Fibonacci heap instead of the normal binary heap.
E plus, say that again, E plus V log V?
Yeah, so I can write that. Yeah, E plus V log V.
But assuming everything's connected, like E and V, E is definitely greater than V, so like we could just call it E plus E log E, which is just E log E, right?
Well, E is greater than V, but we don't know how big log V is, so E might not be greater than V log V, V times log V. And
no, but I mean like we can substitute in E's everywhere instead of V's, right? So this becomes E plus E log E because E is greater than V. Strictly because it's a connected graph. Or it's a connected graph and it has one more edge than a tree. Otherwise, the problem would be moot. So, like, I think it's still just E log E, right?
Yeah, essentially.
Okay.
If you like only take like the really you take big O to its like logical inclusion, upper bounding, because like this is not very tight, right? But yeah.
Sure.
Yeah, but yeah, essentially. So prims and kruskals run in roughly the same time. If you want to get into advanced algorithms, you can you need some more advanced data structures, namely the soft heap, to get it down even more. But as far as we know right now in the big 26, there is no like strictly linear running time for minimum sum spanning tree. However, for minimum bottleneck, as I've just demonstrated, you can exploit the specific structure of the bottleneck problem to get a linear time algorithm. So technically, minimum bottleneck is still easier for now. Like minimum sum, like I said, getting pretty close, but we haven't figured out any new ways to make that faster ever since the dude who came up with soft heap improved the algorithm in like the 2000s or something like that. So it's been a while, but okay. So that's the undirected case. So moving on to the central topic, which is the minimum bottleneck arborescence here. So like I said, there is sort of an asymmetry for arborescences. And so we'll focus on the out trees for our talk here. And so similarly, Camerini's algorithm, basically you add in all of the lower half edges after you found the median. And then essentially you just run some sort of exploration algorithm, let's say BFS, to see, does this form a spanning arborescence? If yes, then you recurse onto the lower weight half, and if no, then you recurse onto the bigger weight half. However, a complication introduced is that because an arborescence is not symmetric, you can't do edge contraction. And so let's say you have to recurse into the bigger half and then have to recurse into the bigger half again. Like you have to like sort of run a BFS starting with all of your edges so far in the worst case. And so the bound of each level of recursion is no longer geometrically reducing. It's big O of M for each level of recursion. Thankfully, you're still doing binary search, and so the number of iterations is only logarithmic, and that's where the bound of E log E is derived from. You're doing O of E work at each level of recursion for at most log E number of recursions, and so you get E times log E, which is where Camerini's algorithm for minimum bottleneck arborescence comes from. Does everyone understand that?
Yep, I think I got you. And just to check, like regarding what you said about us not being able to do contractions here, the idea is like if we have two, like maybe there's a whole bunch of some structure over here, and they're only connected by this node in the center, then like we can't contract these two outer nodes even if this is like a 1 and this is a 1, because like they're pointing opposite directions, so there's no way to traverse over this structure.
Yeah, so like, like you can't get from here to here, right?
Yeah.
And so contracting it would not like preserve that asymmetry somehow.
I'm wondering
So yeah,
if,
so
like, I don't mean to steal like take away from your talk, but I'm just thinking to myself, that's actually really interesting. Like I'm wondering if there's some way that you like contract like this triplet all together and like have like edges on each side like map onto their direct targets on the other side or something, but I don't know.
Yeah,
maybe that's where you're going with this. I'm not sure, but
so technically there is something called a strongly connected component, and the definition of a strongly connected component is that you can reach every other vertex in the component from any other vertex, so they're pairwise reachable. And so technically you can contract a strongly connected component into one thing, but you still have to like dynamically maintain edges coming in and out, and it's slightly complicated and involved, and doesn't really help us at all in terms of trying to find our spanning arborescence. But I mean, yes,
wait,
there are.
But if you reduce everything into strongly connected components, then the graph essentially becomes like a directed acyclic graph, right? And
yes,
can't you like kind of
wait? I don't think it does.
Determine where the root is by doing that, because if it's acyclic, you can kind of like sort it, like do a topological sort is what you say. But yeah, you can kind of determine where the root is. No.
Yes. However, we're trying to bound the worst case, and so it could very well be the case that there's no cycle in our graph, or in case the entire graph is one big strongly connected component, and then you don't want to contract the entire graph into like one node, right? That doesn't really help at all. Is that
right?
Yeah, so we're deterministic algorithms, we're trying to think about the worst case here. But yeah, for a more fine-grained argument, like you like in terms of practical implementation, that could be like an optimization, but it doesn't help in the worst case. If that makes sense.
Thank you.
Is it true that the root of the graph for the directed arborescence is given as part of
Yeah,
the problem statement?
yeah, it's part of the input.
Okay, great.
I was
Thanks.
assuming we had to deduce it.
Oh, I mean, I guess like you can equivalently sort of deduce it, but uh, it's slightly more involved. But yeah, you can stay within linear time and deduce it, but it's not
I
a
mean,
trivial thing, and it doesn't like
for a single graph, wouldn't it be the case that depending on the root, like whether a thing is an arborescence depends, a spanning arborescence rather, depends on not just the graph, but also on what the root is. So for a single graph, if I give you a different root, then I think I would be asking for a different arborescence, would I not?
yes, essentially.
And furthermore,
So
the idea of what's minimal, like what is minimal, even if you could construct the same arborescence as being minimal on one, doesn't mean it's minimal on the other, like up to root changing.
yeah, and so sort of like the intricacy there is kind of hard, and so essentially, if you're willing to not give the root as an input, you need to give something else sort of bound, like what you're trying to optimize. So maybe like you want to find a minimum swarming arborescence below a certain weight, and so find whatever root that gets an arborescence satisfying that weight. But yeah, so if you don't give a root as an input, you need to give some other parameters to sort of bound like which root you're trying to pick, if that makes sense.
Yeah.
Okay, but yeah. Okay, so yeah. Is everyone with me on like why the logarithmic slowdown happens and why we need to do O of E per level, and then we have at most logarithmic levels?
Yes, and that is current state of the art. There's no like clever algorithm that does some.
Okay, so that is not current state of the art, but the current state of the art is slightly more involved. Okay, so and now it doesn't really help my construction at all, but it's good to know. So the current state of the art is by Gabao and Tarjan, and basically for the general case, what they notice is that you can run Dijkstra on it. I know Dijkstra again, and essentially what the cost function for Dijkstra in this case is the minimum edge needed to reach a new vertex. Not the minimum cost, just the minimum edge needed to reach your new vertex. So let me go over on this side. So for normal Dijkstra, the cost of like a new vertex V is equal to like the cost of like reaching like U. I guess okay, that was terrible, right? Handwriting. The cost of like the edge UV plus the cost of U, right? I guess okay, maybe not everyone's familiar with Dijkstra, but essentially, okay, I guess I should ask. Does anyone here not know what Dijkstra's algorithm is?
I'm actually making a video about it right now.
Oh, okay. Is this making sense to everyone? So
what you're saying here is just like I think we're assuming that the edge UV is the one that's used in the final graph here, but what we're saying is like the distance to node U from the root and the distance like the distance to node V from the root is only separated by an edge, presumably like the edge that we select and the cost of that edge.
yeah, so essentially the cost of the next vertex V is the cost of reaching V from U and the cost of reaching the previous vertex U. That's normal Dijkstra where you're trying to find the shortest path. However, we're trying to find the bottleneck path. And so the cost of reaching the vertex V is simply just the cost of the edge needed to reach it. We don't care about how we've reached the previous vertex. We just care about, is this minimum so far? Does that make sense?
I think so, yeah. So
Yeah.
I do kind of want to just try it. So like if we say 1, 2, 3, I'm just gonna book numbers in order. 6, 7, 8. So like, and we're saying this is the root, I assume. I think that has to be the root,
Yeah.
right? So now we run Dijkstra, so we take this node, then like we explore each of the next nodes and set their cost. So we're now setting this one to be cost 1. Is that correct?
Yeah, because it takes it takes on this edge here to reach it, right?
It has to take a length 1 edge. So
Yeah.
then this becomes 2 because the only options are 2 and 3. Then this one becomes 4, which is the min of the 2 incoming edges. Is that right? Then this one's 7, then this one's 8.
And then I think that's it.
Okay. So what does that tell us?
So you just run Dijkstra, and so like, let's see here. So you don't never need this because 6 is greater than 4, and so when you expand this edge here, you see that this cost is already 4, so you just don't add that. And then
so we just delete all edges that don't contribute to the cost of a node. Like the 3 got discarded, the 5 got discarded, the 6 got discarded, and so we just toss the edge.
Yeah, and that's essentially how Dijkstra work as well, right? Which is calculate cost differently. For normal Dijkstra, like you have to add up everything up to the vertex, right?
Yep, that makes sense.
For our model, you just won't care about like the next current edge. Yeah.
Cool.
Yeah. And so for the general case, that is the best you can do. So it runs in normal Dijkstra time, assuming Fibonacci heap, which is E plus V log V. For the case where the graph is sparse, as in the number of edges aren't too much bigger than the number of vertices, what Garbau and Tarjan did was, how we're doing binary search here for Camarinis? What they did was essentially exponentially increase the number of partitions. So for binary search, you're partitioning the set of edges into 2 halves, right? What they did was just exponentially increase the number of partitions. So recursion level 1, 2 partitions. Recursion level 2, I think like 2 to the 2 partition, and then recursion next level down 2 to the 4 partition, and so on and so forth. And so doing that, what that allows them to do is they don't reduce the number of work per level at all, but they do reduce the number of recursion levels from logarithmic into the iterated logarithmic function. And so you get a runtime of E times iterated log of E. And just to quickly define the iterated logarithm function, it's this log star of n here, and what this is 0 if n is less than or equal to 1, and log log star. Actually, my bad. This should be 1, I think. Actually, is it? Yeah, no, it's 0. No matter. Okay, log star of log of n plus 1. So essentially, it's the number of logs you need for n to reach 1 or less. So by exponentially increasing the number of partitions that they're searching over at each recursion level, they're reducing how many recursion levels you have to go through. So instead of 2 partitions, you can imagine like just a bunch of little partitions, and then they use Dijkstra to sort of like, okay, merge 1 partition in, merge 2 partitions in, merge 3 partitions in, and then
what do you mean by merge?
That way,
merge a partition in?
It means like just run, like add the edges to Dijkstra and then run Dijkstra. I guess. Okay. It's a little hand wavy, but it is like pretty complex.
Wait, so we're running on the outermost layer. We're running this Camerini, if I'm getting the name right, Camerini's algorithm. But on each iteration, we do this Dijkstra thing, and like, so like step one would be: are we still bifurcating it by 1 on the first step?
Yeah.
Okay. So for step 1 in this graph, it would be like, I'll say like 5 maybe is the median, and then so we would cut out all the other stuff, run Dijkstra, fail to produce an arborescence, and then the next step is that we put in
at the next partition in, and then run Dijkstra on like the halves we didn't cut.
The halves we didn't cut. What is a half we didn't cut? Like, so hold on. So we got this. Like, what is the actual second step? You drew a lot of lines there. I don't know if that was actually meant to reflect reality or not, but like, what's the...
Okay, hold on. So like, instead of like, so Cameroon is doing a binary search at every level, right? Yeah. So for Gabao and Tarshan, what they basically did was just exponentially increase this. So I think this is like 2 to the 1, and so like I don't know, like the next level is like 2 to the 4, I think. So that's like 8 partitions. How much is this for? Split that. And so basically
we run Dijkstras on each of these tick marks.
Yeah, and so basically run Dijkstra on this, no spanning tree, run Dijkstra on this, no spanning tree, run Dijkstra on this. Does that make sense?
I don't see how that's an improvement. Aren't you just doing more work? Wait, are we saying like so? Let's say there was an arboration here that we did find. There was one, meaning the bottleneck is somewhere in this segment, right?
Yeah.
So like, why are we even generating these?
Oh, my bad. No, I mean, like, imagine like if this is.
Like, okay. I see.
Yeah. Recur.
Gotcha. So okay. Continue. Sorry, I'm with you now.
Yeah. So yeah. Essentially, yeah. You're just like exponentially like increasing the number of partitions to get like a finer grained like partition of where the bottleneck is, because like let's say like up here, like you can only split it in half, and down here like the bottleneck is like, let's say like here, then you only need to like work up to here instead of like having to even care about these.
And importantly, the ones on the right are the more computationally expensive ones. Like evaluating this tick mark is more computationally expensive than evaluating this tick mark, right?
Yeah. And yeah, by exponentially partitioning at every step, that's how they derive their iterated logarithm. And what iterated logarithm is just the number of logs needed to reach 1 or less. And you can sort of imagine how that pops up in the analysis for this thing, right? Like,
what does that function actually? Sorry, what does that function actually look like? Like.
Oh, I've written it down here, but maybe like.
No, but I mean, like, what does a graph look like?
Oh,
it's very slowly.
Okay, like
slower
than
base
log.
10, right? It reaches 1 at 10.
Yeah.
And 2 at 10 to the 10, and 3 at 10 to the 10 to the 10. It's essentially the inverse of a tetration.
I see. Okay, thanks.
Yeah, so like for like practical purposes, you can consider it constant, but yeah, it's
slower than like, log, but faster than inverse Ackermann, if I'm getting that right.
So actually, I think inverse Ackermann is still slower growing than iterated log, but yeah, iterated log is like just like one tiny step up from inverse Ackermann.
Yeah,
it's between those, yeah.
But yeah, so and essentially yeah, and so that's the current state of the art. It's either Dijkstra or just a general graph, and mostly dense ones. Then for sparse ones, you run this extra search phase to get iterated logarithm. Yeah, but so yeah, those are the current state of the arts. And there's, I guess, a more restricted case for that was actually pretty recent, like I think 2024, where basically someone just realized that if we restrict all the weights to like bounded integers, you can just do some linear sort on it, like radix counting, pick your favorite, and then just do like a linear search on the edge weights. So like just add edges one by one by one in like growing order, and then stop when you reach a spanning arborescence. If that makes sense. And like you can imagine, like if you had an actual sorted order and not just like two partitions, then you can just add edges, essentially crucibles for spanning arborescence, if that makes sense.
I think I follow.
Yeah. We've just been avoiding sorting them up until now because sorting is more expensive than the runtime we're going for. But if you can sort them for free or for linear time, then it's easy because you just add them from the ground up. Yeah.
Yeah. So yeah, sorting would be E-log-E. However, like I said, if you can have a sorted list cheaply, then you can do it by cheaply, I mean within linear time. And you can, if you restrict off the edge weights to some bounded integer, then then you can do like counting sort on it, or maybe radix sort, and then just add the edges in one by one by one until you find the bottleneck edge. So like here, yeah, if you can add the 1, the 2, and then the 3, the 4, and then the 5, the 7, the 6, and then the 8, and like, oh, yep, now there's a spanning tree, and so the bottleneck edges has to be the 8, and then it doesn't really matter what the smaller edges are, just find some spanning.
Well, how fast is it to check if you found a spanning arborescence?
You're just essentially doing like that's actually a good point. So one of the sort of component I need for like the algorithm I'm trying to work on is called incremental expansion, or incremental BFS specifically. And essentially, as you're adding edges in, you sort of like do BFS in stages.
Right. So you're maintaining a tracked list of like where you get stuck, and just save that like boundary set, and then add another edge, and then see if anything is now touching the outgoing from your boundary set.
Yeah, basically you add this edge 1 in, and then you're like, okay, I can reach this. Can I reach anything else yet? These edges haven't been added yet, so no. Then add the 1, 2 edge in, and so forth and so forth. Yeah, and then and then you just like keep track of which ones you have reached and which ones you haven't. And then when you add an edge between like a reachable that goes to an unreachable one, you're like, oh, this is new reachability, and then start a BFS from the one you've just reached.
Yep, makes sense.
Yeah, and essentially, you're not sure because you're not sure like which the specific amount of work of each edge addition, because some edges trigger another BFS run, some edges don't. But if you amortize that over all of the edges, then you're never doing more than the amount of work that regular BFS would, which is linear.
Yep.
Yeah, and essentially, with linear time integer sorting, and when you bound the weights like that, you can get linear sorting, and then you can just get BFS. All right. So that's all of the current state of the art, and so that's been pretty much the case. So what you've noticed so far is that all of these algorithms get pretty close to linear time, but not quite, right? So the natural question to ask is like, if we want to improve this, how much should we improve it by? And so and the ultimate goal is linear time. So, and the reason why we don't expect to go below linear time is via a pretty trivial lower bound we can derive, which of just omega of e via like an adversarial argument, which is that you need to at least scan each edge once, so you can make sure that you haven't like missed like a potentially cheaper edge to reach some vertex.
Yeah, it seems like validating something even is an arborescence is. Oh no, yeah, that doesn't work naively because potentially the set of edges is much larger. So you need to actually scan over not just the edges that are included in the arborescence, but all of the ones that you didn't include as well.
Yeah, to make sure like
Yep.
I'm if this vertex with an edge of weight 3, but I need to scan all the other ones to make sure there's an edge of weight 2 in there somewhere.
Yeah, that makes sense.
So yeah, so just via that simple or like adversarial argument, like you can derive an information theoretic lower bound of omega.
Yeah, you have to make sure there's not some like 1 billion hiding somewhere in your edge set, so that you can get rid of it.
Yeah,
because that would be the bottleneck immediately.
Yeah, and so essentially that's like the best lower bound you can get, but none of our algorithms so far reach like true linear time, and so purportedly I can try to construct one. Let me see if I can explain this best. I don't know if we'll have enough time for all the intricacies, but hopefully we should have enough time to at least get to like the first half of my construction. So going back to Camerini's so let me see here. Let's try to use this. Okay, so we noticed that Camerini has to like run this whole thing for O of M, right? At every recursion level. So the natural question to ask is, okay, like, can we try to do less work? Because Gabao and Tarjan tried to do fewer recursions, and the best they got is iterated logarithm. So that's probably stretching it pretty far. So can we try to do less work per recursion? And the answer is, as we just demonstrated, it is possible with incremental BFS. So instead of doing this entire work here, if we can just remember what vertices we've reached so far, then instead of doing this whole chunk of work again from scratch, we can just only do like add in the new edges, and then get rid of like this stuff here.
That makes sense.
Yeah, and so essentially, if you're only ever adding edges, then this will amortize to linear time. So for the incremental case, where you don't expect to overshoot, you don't expect to have to backtrack to like because you've added too many edges, then this works. This is hopefully everyone should see why this is clearly linear, because this is just another BFS.
Yeah, you're adding a length 2 of BFS time, I guess. I don't know how you'd say it, but I'm saying this is 1, and like time, the amount of time you spend is just the distance in the x direction that you're going. So yeah, that makes sense.
Yeah, right. And so the complication comes because sometimes when you're recursing, you add too much, right? And you're like, oh, I form a spawning arborescence. I don't know if this is exactly the amount I need. I might have added too much, and so I need to like recurse it to the smaller half. And then you're sort of in trouble because like you need to sort of like figure out, okay, like I need to delete these edges, but like if I delete an edge that like disconnects some number of vertices from my root, then I need to like propagate that change, and then that change might propagate to all the vertices, and then worst case, you're still having to do like a lot of work.
Yep.
And so, in fact, quadratic work, which is not good. So, how do we fix this? Okay, So now we need to go back and say, okay, how were we maintaining our reachability like tracker for the incremental case? And so a simple way to do that would just be like an array of bits, let's say 0, 1, and then because okay, or I guess like a hash map might work better, but that's there's leeway there. Essentially, you just need a constant time query, and then for the size to be at most linear, so not too bad. And then so you have this data structure, let's say R, and then an easy fix to this would be just to keep a separate backup copy of R, let's say R prime or something. And so anytime you finish adding vertices and you haven't overshot, you save R to R prime. And anytime you're traversing with R and you're like, oh, I've added too many edges, instead of trying to delete edges, you just revert everything back to R prime. Does that make sense? So maybe like
yes, the copy operation is O of E or something though, right?
Yeah, it's O of V, because you're not the R structure doesn't care about edges. We only care about vertex reachability.
Okay, yeah, sure.
Yeah, and so like for example here, like okay, like we try to add this in, but like, oh, this forms a spanning arborescence. We might have added too much. We need to recurse into half here, and so that's this much work, and we need to reset, and then recurse into half here, like this much work. We need to reset, and the reset there is hiding an OV work, because you need to go through the entire like copy operation for R here, sort of reset R. However, this is still an improvement over vanilla Camerini, because vanilla Camerini is E log E, right? So if you imagine, like, the number of edges is geometrically shrinking here, so our procedures that depend on edges is fine. That's clearly linear thanks to the geometric sum. However, we might have to recopy R at every recursion level. And so worst case, that's actually a V logarithmic number of recursion levels. And so that gets us E plus V log V, which is equivalent to the Dijkstra without actually having to use like a Fibonacci heap at all, which is very nice. And
just to make sure I'm with you, the terms here are coming from where exactly? The log V is the depth of this, like, this
recursion, and the V is coming from like the maintenance of this copying, right? We might have to like recopy R after every recursion level.
Why is this
the V?
Why is this not log E?
Yes, it is technically log E, but for connected graphs, V is greater than E. I mean, less than or equal to E less than V squared, right?
Oh, so we can call this V squared and then pull the 2 out.
Yeah, essentially.
Okay, cool. Wait, why is it V is less than or equal to E? Okay, so we're assuming no like double edges or anything, which I think is a fair assumption.
Which if like you can like turn any multi-graph into a graph which is linear pass.
In
so it's
OV time. Yeah, that makes sense. Okay.
So even if we weren't given a simple graph, we can make one. So.
Yep. Okay, so I'm trusting you on log V. That makes sense. What were you saying about V? I cut you off.
Yeah, V is the time to do like the maintenance on this structure, right? So you need to potentially, worst case, need to like recopy it at every level, recursion level.
V is copying forward and backwards, and both of those are included there.
Yeah, I mean that's just O of V for one and O of V for the other, so O of V total.
Do we actually need to copy 2 R prime? So like in this first step, like up here in this step 1,
yeah.
Can we just like write to R prime at the same time that we're writing to R? I guess that's just de-amortizing it, maybe. So maybe I guess it doesn't make a difference.
We don't want to like have to figure out like, okay, which vertices we've changed in this interval. Yeah. We just want to like hard reset to here.
Yep.
And so we don't want to R prime yet.
Yes. And we're always doing this at the halfway mark. Is that the rule?
Yeah. So it's like we've figured out that this does form a spanning arborescence, right?
Yeah.
And so we need to do binary search by splitting it in half and like figure out, okay, does this spanning arborescence?
So like as we're inducing things into the node, or sorry, into R, like as we're adding edges into R, when we get to the halfway mark, we copy R to R prime, then continue adding things into R, and then you evaluate the status of your arborescence, at which point you either continue or jump back to this.
Yeah, okay, so maybe like phrasing it in terms of recursion a bit better. So, okay, so so you split it in half, and then you're like, can I add everything in here? If the answer is yes, then you might have added too many, so you need to reset to the previous R prime, then only add half. And then is the answer still yes? If the answer is no, then you can add everything here to R prime and then recurse half here.
Yep. Yeah, I got that. I was just trying to make sure I understood where your precisely where your copies are taking place. But yeah, I think I'm with you.
Yeah, so you don't need to copy when you're incrementing, but when you're decrementing, like potentially deleting edges, then you need to reset to a previous copy.
But you have to write to R prime at some point, which is the halfway mark.
Yeah, the halfway mark.
So you're copying in both directions, right?
Yeah.
Okay.
It's just that for the reset, you need to like recopy it kind of twice ish.
Yep.
But yeah, it's OV work either way, and for logarithmic iterations, it's V log V.
Where does the E come from? I forgot already.
The E is our binary search here. Linear time median finding is linear in the number of edges we have left, right? The number of edges we have left is geometrically decreasing.
The number of edges.
So
yes. Yeah.
We thought E edges, and then we recurse into E over 2, and then we recurse into E over 4.
Right. That's the amount of edges that we're going to have to run incremental BFS on.
Yeah, and also, like I said, median finding to do our binary search.
Sorry, what is median finding?
Well,
to find the median, it takes E. Yeah. Okay. Yes.
Yeah.
Gotcha.
So so this is pretty clear so far. Hopefully, this is not the next half is a little sketchy. I haven't fully convinced myself yet, but essentially, the copying operation is sort of like our main cost now, right? Everything else is like clearly O of E now. It's the copying operation that's costing us this V log V factor, right?
Yeah.
If we can somehow try to reduce this, then we're in the clear. We're O of E time, right?
Yep.
And so what I've been trying to do is instead of like adding edges this way and then testing for spanning arborescence, we can try to like go deleting this way and seeing, okay, like do we strictly need this edge after like when we're trying to delete it. So essentially, let's see here. We have some edges coming into a vertex here. And I'm saying that, okay, if all of the edges coming into a vertex here is from the bigger half, then clearly we can't delete the bigger half. Because, then we wouldn't be able to reach this vertex anymore.
Makes sense.
Yeah. And so essentially that helps. That guarantees like the case where the bottleneck is in the bigger half, then we're in the clear. The case where the bottleneck is down here, it's a little more intricate. Essentially, I need to argue that, okay, when I'm deleting edges, I'm able to find this smaller in edge down here, and then figure out does the in edge come from like a cycle. So to avoid like the case where like, okay, this in edge doesn't actually help the root reach this vertex. So essentially, like, you know, it might be the case that, okay, this is from the bigger half, but like this is the root here. So, you know, you don't want to delete this. Even though like this, like, so this is 1 and this is 4 or something. Even and this is like, I don't know, 5. And then you know, I need to argue that I can figure out like when this is the case. So like, you know, when like when like the bigger weight edge is actually necessary for reachability. And in order to do that, it requires like just hopping back and seeing, okay, does this connected to this back edge connected, going back on this edge get me to like eventually get me to some vertex that's already reachable, as opposed to this, which might like only lead me to like an unreachable cluster. So let me see here. Let's copy over these guys and okay. So like, you know, let's see here. Swap these over. Let's say this is 6 and this is 4. So you know, essentially I need to argue that I can figure out like this 4 here, even though it's cheaper and potentially in the smaller half is like can be deleted, while this more expensive edge here can't. And by essentially just going back and figure out, oh, the root is reaching this vertex already, I probably need this, don't delete it. Does that make sense?
You're saying we can't delete the 6?
Oh, I guess like in this case it would be the 5. Yeah.
Why can't we delete the 5? We can. Oh, you mean after we've deleted the 6, then we need to keep the 5?
Yeah.
Sorry,
so
say that again. What? How do you conclude that? Like.
So like, okay. I mean, I guess like just to convince you that we can't delete the 5. Like clearly we delete the
right.
The 5.
Yeah. That disconnects the graph.
So basically, okay, like when we're trying to delete this, we're like, okay, go back. Is this thing reachable? And then, you know, clearly like this must have been added after this, right?
Yeah.
And so we've done our incremental BFS on this and marked it as reachable.
Yeah.
And so we just go back and like, okay, is anything here reachable? Is anything here reachable? And then, you know.
When you say here, what do you mean? Is anything like where I
like? So it's like go back. Is this reachable? Like, let's say go back. Is it reachable? You know.
From what? Is it reachable from what?
From the root. Which spanning arborescence.
But if we're running a BFS already, like, don't we already know that it is?
But we're trying to go the other direction, right? So, like, let's say
so we're arbitrarily picking like high edges. I guess I don't know what context this step is being run in. So like, it sounds like you're saying like maybe after we've already run the half step here, then like we're doing the second half, which involves just picking the highest edge we can come up with, like trying to delete it. And if we convince ourselves that we can, then we do. And if in the case of 5, like the way that we try and do that is we just look at the edge that we're concerned with, take the thing that it's pointing to, and see if without the 5 it's still connected upwards to the root, via any path, not necessarily by the, well, obviously not by the path that we deleted. And in this case, you know, this cut does separate the 4 from the root. So we determine that.
Yeah.
Okay.
And so basically, essentially, anytime we're trying to delete edges from the bigger half, we need to like make sure we're not disconnecting it by figuring out like, okay, is this like is this a cut that that's going to like, you know, destroy our reachability?
Yeah.
Yeah. Yeah. Alternatively, you can just like, okay, is this a cycle? You know, because if it's alternatively, you can like, okay, there's a cheaper edge here. I could keep it, but it forms a cycle and doesn't help with my reachability. So, like, okay, let's keep the next cheapest edge. Does it form a cycle? No, it doesn't. Actually, yeah, it doesn't. Yeah, it doesn't form a cycle with this thing. So yeah, so I can keep it from the root.
Yeah. Okay.
Yeah, and so basically, yeah, I'm still working out the intricacies for that, but essentially, yeah, instead of adding edges from bottom up, we're trying to delete edges top down, and
we're doing
figuring
both
out
of those, right?
Yeah.
Okay,
So essentially,
so walk me through the two cases here. Like either we do see the thing at the midpoint, or we don't see it, or like we do have a arborescence, I mean, at the midpoint, or we don't.
Yeah, let me try to argue a bit more in depth here. Okay, so we've found our median, and now now let's say via our I'll call it pruning procedure here.
Yeah,
we try to delete some edges, and you know, we say, oh, this edge is necessary, we can't delete all of the bigger half, then we know that, you know, the smaller half has to be included in the can be safely included in the final tree, right?
So you start by pruning. Is that what you're saying? Step one is to begin by pruning going this way.
Yeah.
Okay.
And then if it says no, prune failed, then we know that the smaller half here can be safely added because the bigger half can't be all deleted. So you need the smaller half and some part of the bigger half to form a spanning arborescence. And so,
if we fail to prune, then we get to add this for free. Yeah, I agree.
Yeah, and then we split it in half, and then we try to prune like the smaller half, like this reduced half again. And then if the answer is still no, then we get at this for free, essentially.
Yes.
And however, if the answer is yes,
then that means that the bottleneck is in here.
No, that means the bottleneck is like.
Oh, sorry.
In here.
After you mean after so, yeah, after we sorry, I was talking about if we prune this. Yeah, if we prune this and the answer is yes, then that means that the bottleneck's here. Yeah, I agree.
Yeah, and so we can discard this. So either way, we're reducing our current working set of edges by half.
Yep.
Yeah, so we're always reducing it by half, so that preserves our geometric series. And pruning doesn't require us to keep a connection to like the already discarded edges, whereas adding edges like bottom up does require us to like potentially have to like revisit stuff by keeping this copy.
I think so I see where you're going with this.
Yeah, so basically by doing this pruning procedure instead of like incrementally expanding bottom up, we don't need to keep a backup copy because we're never over adding to our set, right?
Yes.
And so we can get rid of this work here.
Right. So like the max work that we're ever going to have to do here is either like complete traversal in this direction or complete traversal in the backwards direction, or some between the two that like, but like at any given like X distance on this plot here, you're only ever going to be tracking over like a little bit in the X and a little bit in the, a little bit in the positive X and a little bit in the backwards X direction. So like you're still bounded by 2e.
Yeah, so essentially
you're doing.
We're doing like at most 1e of work this way, and we do 1e of work this way, and they meet in the middle at some point, and then eventually it all adds up to advertise O of E.
Okay. Yeah. That I think that makes sense.
Yeah, and the point is precisely the bottleneck edge.
Right. Yeah, you're going to converge the bottleneck edge. Oh yeah, you're never going to go past each other.
Yeah, that's the whole key as to why we don't need to maintain the copy anymore.
No, but wait, you do need. Sometimes they do pass each other because like if you go like this, well, but you start by. Do you have to start by pruning? Does it even matter which way you start by?
Yes, because you're trying to. The pruning decides which half you recurse into, right?
Okay, so if we prune this way, and we fail to find the arborescence, that means that we're stuck.
That means that
we're
stuck. That means we have to recurse into the bigger half, and then we can add the incrementally for free.
We get to add this for free. Then
yeah, we still need to do BFS and everything.
So like, what triggers you to start doing upwards BFS? Well, we add it for free, and then
when the prune fails, right? No, add it for free just means we get to decide to add it for free. So we don't need to maintain like a copy of R. We still need to maintain R.
Yes, you maintain R, but you don't need R prime because you know for sure that it's all going to be there.
Yeah, and so essentially, this is just trying to get rid of the copy operation. So whenever.
Yeah.
I don't entirely want to interrupt TwoSwap's questions, but I will just note that I think I understand the overall setup, but I don't think I understand the pruning algorithm itself.
Yeah. Let me see if I can best explain this. Essentially, if there's a big edge going into an already reachable vertex, we don't care, right? Because that vertex is already reachable. This edge doesn't really affect anything. So like, we can safely delete it. So the only case where
already reachable, you mean reachable in the copy, right? Like, how do you know it's already reachable if you're not?
Yeah, we're maintaining R.
Copy.
We're maintaining R here, right? So anytime we incrementally do BFS, we already have a tracker of which vertices are. Hopefully that makes sense. Like,
okay, so we ran stage 5 and it marked like a bunch of vertices as reachable or something. And but it still wasn't enough to make the arborescence. So then we run stage 6 and it marked like a bunch of new vertices as reachable. But it was already an arborescence. So stage 6 put in too many. So now we need to like prune stage 6.
Okay.
And I guess
I think you're complicated, confusing the order a bit. So you always try to start with the prune, because the prune sort of decides whether you incrementally expand the smaller half or not. So like if the prune succeeds, as in then you could recurse into the smaller half. If the prune fails, then you recurse into the bigger half.
Sorry, what does? I don't.
So essentially, the prune is trying to delete edges, right?
Yeah, and so I agree.
So if you ask your deleting edges, if you determine that you can safely delete all of the edges in the big half, so like these two, although this specific example is a little sketchy, but essentially, let's say like no, these guys, like let's say you determine you can safely delete these guys, then you know that okay, everything smaller than these guys in the smaller half can be safely added. So you incrementally do BFS on all the smaller weight half, then mark anything you can reach. Actually, yeah. wait. Okay, I think I might have messed that up. Oh my god. Okay. Okay, okay. So basically, you're trying to delete all big weight half, and determining, okay, can I safely delete this without disconnecting a vertex from the root? If the answer is yes, I can safely delete everything, then I just discard the bigger half and then recurse into the smaller. If the answer is no, and then like I find this edge here, and like, oh, I actually need it to reach the root, then I know that actually I actually need it to reach the root. Then I also know that I can't delete the and then here.
You start with essentially you start with everything in the set, and you only try to delete from the top, more or less.
Yeah. So
then you sort of delete the biggest piece you can.
Yeah. So instead of adding edges bottom up and seeing, okay, have I formed a spanning arborescence? I'm basically deleting top down and like, okay,
yeah,
as I'm going, do I need these edges for the arborescence?
Okay, and when do you do BFS? I guess is the part that I'm more confused of. Is that I'm sorry if I'm retreading ground you've already done.
Could we just hopefully this will help all of us, but could we just run the algorithm on this graph here?
That sounds reasonable, yeah.
Okay.
Yeah.
So
the what's the median here?
First of all, yeah, I'm just gonna I think it should be like between 4 and 5, but I'm just gonna write
It'd
it
be
out.
either 4 or 5, so we have to tie break somehow. I don't know if it matters how you tie break.
Yeah. Well, I imagine we just delete the upper half, right?
Yeah, so
we'll
so for medians, we try to delete this.
Including 5, right?
So, yeah, including 5. So just imagine we're disconnected.
Sure. I'll just go ahead and delete.
Awesome.
Delete. So now we're running the pruning step. I don't think you actually really said explicitly what we're doing for the pruning step in terms of like if we're deleting multiple things at once. So like, what node do we start with here? Like, what do we do exactly?
Yeah. So essentially, so as you're deleting it, you're keeping track of like, okay, is there any like origin that is reachable? So let's say like.
Oh wait, so sorry. So we're moving backwards from 8 and deleting each one of these individually. Is that correct?
No. So okay. Let me try to explain this better. So like when you're deleting this edge, let's say 8 here, you're trying to track. Okay, is this already reachable?
I guess reachable from what BFS? We're at the very beginning of the algorithm, so I guess I don't know which BFS
so the answer is
done yet.
The answer is no, because we haven't run BFS on anything yet, right?
Oh, okay. Well, I don't know, but okay. So nothing is reachable right now. Everything is unreachable.
Yeah, except with the root. We always start with the root mark.
The root is reachable. Nothing else is reachable because the set of things we've done BFS on is empty.
Yeah. So essentially, you need some way to, right? So basically, once you deleted all the edges, you basically try to see if anything's disconnected. So like, from the root here, you can go here, but you can't go further. And like, you can do this without actually having to touch this at all by just like keeping a counter. So like, how many have I reached? Boop, boop, boop. And that only takes a logarithmic number of bits in terms of the vertices. So log V to like, reach, add 1, reach, add 1, reach, add 1.
It doesn't do it. Doesn't doing a full BFS take V time? There are V vertices we have to touch. It doesn't take V memory, but it takes V time.
Yeah. Yes, but if we get rid of this we can do a count, and then we can sort of like okay, let me phrase this better. So basically, it is v time, but if we actually manage to reach everything, then we're kind of done. So like by some assumption, like it should be disconnected because okay, let's say like we get rid of
reach everything, we're not done, because if we reach everything, we know we need to delete more edges, right?
Yes. Oh, okay, that sounds a little sketchy. Let me see. Yeah. So as you can tell, I've been spending most of to get that bound, and the later half of my algorithm is still in progress. So bear with me a bit here.
That's okay.
Yeah. So essentially, yeah, you. I guess my assumption is so. I guess let's maybe like try to ignore the base case for now. It's a little sketchy, but let's assume that okay, like we can mark these as reachable.
Sure.
Hopefully
Okay. We run BF. We delete the things above the median. We run BFS and we mark everything that's reachable as reachable.
Yeah, and then we realize, oh, only these are reachable, and so we're like, we're like, okay, we don't need these edges. Okay, we do need these edges. My bad. And so we're like, okay, undelete all of them. Find the median, which is like I don't know 6, and then only delete edges.
Yep. So now we're here. We delete 7 and 8. So cut out these two. Now we run BFS again. And
but we start from here.
But starting from there.
Because we marked these as reachable previously. So
yes.
Yeah, and so basically
and then now we get to that node.
This bad.
But we don't get any farther, yeah.
Yeah, we don't get there. We're like, okay, we still need at least some of these. So we undelete them.
Yep.
And then
we like undelete 7 and then we reach everything and now we're done.
Well, actually we still don't reach everything because we don't reach this bottom one.
Oh, you're right. Sorry, good point.
And so we're like, oh, still need this thing, and then
Okay, this is a very sadistic graph to be running this problem on. Let's come up with a better example. Maybe I should here. Do you mind if I erase these numbers? I think we all understand this case, right?
Yeah, I guess this was only undeleting, and I sort of want to see it go both ways, ideally, but that might be hard to set up.
Yeah, I feel like the more edges you have, the easier it is to construct such a situation. Like if you have a giant click, like then you're always going to be removing a lot of edges. So, but I guess let's just make let's put the 8 obviously in a spot that can be deleted, and same for the 7 and the 6, and I'm also going to add an edge here for 5. Because we can also delete that. And then 4, 3, 2, and there's no 1, so
I guess
this is a 1. Oh.
That's what we missed.
And this can also be a 1. They don't have to be unique, right?
Sure. Yeah, I think that's true. So we still just get 1, 2, 3, 4, 5, 6, 7, 8. I'm just going to use the same list as before. And okay, so now we do the same game. We cut out the 8, the 7, the 6, and the 5.
Right.
I think you don't even need to write that though, right? The extra 1, because either both.
The median of 1, 1, 2, 3, 3 is 2, right? Or
no, but
it's the whole bottom half, it's a median, right? Where I don't know, maybe it doesn't matter. I guess you're right. It doesn't matter though,
because we're either deleting both of them or neither of them to shrink the bottleneck.
Yeah, so it doesn't matter. Yeah, that's fair.
This is like a best case graph for us. Literally deleting upper half gives us a spanning arborescence. Oh my god.
Well, yeah, but we still we still haven't confirmed yet that it is a.
Yeah. Although I mean, yeah. I guess like we haven't confirmed that it's minimum yet, but yeah, it is a smarting arborescence.
Yes.
So we're like, okay, just forget about the upper half.
Yeah. Okay. So these
So
are
we
permanently
really delete them.
banished, and now we're
Yeah.
Now we say, okay, what happens if we delete 3 and 4?
yeah.
Yeah, what happens if we delete like 3 and 4? And then we're like, oh, we
We
can't
could
reach.
rerun all of BFS, but we're sort of not allowed to do that because that's too expensive, essentially.
Right. We already ran
So-
BFS once.
Yeah, so so like, we're deleting an edge from like a reachable to a reachable means we might be making this unreachable, right?
Yes.
Indeed.
Which in fact is the case. And so we're like, okay, find a replacement edge. Is there any replacement edge? This one's deleted. This one's deleted. There is no replacement. Oh, this is unreachable. And so we're like, okay.
But in the worst case, find a replacement edge just means do an entire additional BFS but backwards, right? We haven't actually saved any time over doing BFS but forwards, I think. But maybe I'm missing them.
Well, okay. Well, actually, no, because
There
okay,
could be
like
some very long path or something.
yes, but that other long path needs to also be reachable already, right?
Indeed,
So like,
yeah.
so like let's say we delete this, and then this thing we can also come in from here, but thing isn't reachable yet. Then like that doesn't help us.
Interesting.
I'm wondering.
Yeah, so
Okay, that's interesting.
so we can sort of stay local to the one, to just the destination we're deleting, if that makes sense.
Right. Well, I guess it could be that if we knew the status, I think here's how I'm thinking about it. If we knew the status of every other node, then we would be in the clear, right? But the problem is we may not know the status of every other node for the same reason we don't know the status of this node. We sort of don't know whether this node has just become unreachable or whether it has not become unreachable because there's actually some other path.
Yeah. So let's say let me see.
But wait, even if we run BFS multiple times here, it's still okay, isn't it? Because like we still end up with the geometric, like convergent series.
Yeah. Yes, for the edges, but not for the vertices. Which because if we still have to do v every time, and that's still v log v.
How do you arrive at that? How do we?
So,
we don't have to do it every time, do we?
Like if it's
Oh, sorry. Yes. No, you're right. You're right.
Yeah.
If each time
so
we
the number of edges is geometrically decreasing, but the number of vertices is staying constant, or the same. So so we would like to tie our performance to the edges instead of the vertices.
Yes.
And essentially, what I'm arguing is that whenever we delete an edge, we can stay local to its destination. And in that case, the worst case is we have to view every in edge once, and then every edge can only be an in edge for one vertex. And so the worst case is we have to like run each edge once. So like we delete this.
An in edge. Like if a guy has 3 in edges, right? We might consider deleting each one of them, and that might each time consider you would then have to consider each other in edge. So I don't think it's true that you have to consider each in edge only once.
Okay, so so let's maybe that's a bad example. Let's say this guy, right? We're trying to delete 4 here. We're testing, is this reachable? We haven't deleted 3 yet, so this says yes, and so actually, okay, maybe let's add like a backup here. Okay, so we're deleting the 4, and then we're like, okay, is there a replacement? We have this replacement, and is this reachable? Well, it was reachable. We haven't updated anything yet, but it's reachable right now. So we're like, okay, replacement found. We can delete this.
Okay.
How do you?
And then when we get to like the 3 here, this you undelete 3.
Yeah, I did undelete.
Okay, we're gonna get when we get to the 3 here. Okay, we're like, okay, this is unreachable now. Because there's no replacement left, and so we're like, okay, propagate the change, and
how do you know for sure that wouldn't this algorithm as described potentially leave you with like abandoned cycles? Like if we try and delete this edge, like we would consider this node and say, oh, there is, like locally speaking, we don't do any search and we locally determine that, oh yeah, there's one more in edge, so it's safe to delete this edge here. But in reality, globally, that leaves you with a disjoint cycle.
Each one of those 3 would say, oh, well, there's still a reachable guy from me. So none of them would be marked unsafe.
Yes. I let me see. I think okay. Yeah.
It seems like you
yeah.
need some amount of global awareness.
Yeah, so we impose the global awareness by only keeping a tree instead of all the edges. Hopefully that makes sense. Okay. Yeah. So when
You're
we're
Go ahead.
so when we're adding edges in, when we're doing our incremental BFS, right? We only keep the actual BFS tree and not and try to not form a cycle. And so that should hopefully resolve that you presented there where there was a cycle.
Right, we'll initially conclude it's okay because everything is reachable, but then later we'll say, well, we have a cycle, so we should get rid of any cycles. And then once we eventually get rid of the cycle, then everything will clean up and we'll say, oh, it's actually now it's disconnected because...
But does that easily informationally propagate back to our earlier decision? Like, do we know from that it was this edge that we shouldn't have deleted?
That does seem tough, actually. That's a good point.
So what I'm saying is that when we're adding incrementally expanding, right? Like either this edge, actually, this we have to keep these 2. This edge shouldn't exist,
right?
Because we're only keeping the tree and not every edge.
Yes.
So this degenerate case shouldn't ideally happen.
Right, but like if we start, like if this is like 4, 3, 2, 1, like we start by cutting out the 4, and you can imagine there's a couple of extra edges that like makes that the actual midpoint, that we cut the 4 and we don't cut the 3 or the 2 or the 1. It's like we attempt to cut this and we succeed and we delete that edge, and like you're correct that like this is something that we want to eventually discard, but for now we cut that 4, and then only later will we realize, oh, we can't cut this, oh, we can't cut this, oh, we can't cut this either. And then how do you come back to the information that this was an incorrect choice? Like how do you...
Okay. So you're saying like we've already marked these as reachable, I guess.
Yeah.
Not?
I think so.
Okay, so you're saying like we've already potentially marked these, therefore we might wrongly consider this as a safe to delete edge.
Yeah, right. We would consider this safe to delete because like there's already like we look at this node locally speaking and we say, are there safe to delete edge or safe to delete nodes that have an arrow pointing at me? And it's like, oh yeah, here's one, like this node here is pointing at me and it's safe to, like it's safe.
Okay, so I see. Okay, so I mean, like, I guess what I'm arguing is that if these have been marked reachable, right?
Yes.
Then like we've already gotten rid of this guy. Does that make sense? Because we've run incremental BFS on everything here, and we're like, oops, we've.
When you say we've gotten rid of it, what do you mean precisely? Do you mean we haven't induced it into R, or do you mean we've proven that it won't be in a minimal tree, or?
Yeah. So essentially, what I'm saying is that this forms a cycle, right?
Yes.
And so
right. I
when
get
we're
it. I
running
get what you're
BFS,
saying. Like that through BFS, we'll identify this as a path that walks us to the end. But like, are you suggesting that means we can discard this straight up without thinking and like never consider it again? Because I don't think that's correct.
Because we don't know we won't need it later. We might,
Right.
like if we delete
like
3, then the one edge might become relevant.
yeah, because if we're still running, then that means we haven't found the bottleneck yet. So like both 1, 2, 3, and 4. Well, okay, yeah. Both 1, 2, 3, and 4 are not the bottleneck, right? Because we've run incremental BFS on them. And so we know that like even if everything here is 4, the bottleneck is some edge greater or equal to 4. So we're not hurting the bottleneck, right? Even if we get rid of the 1 here.
Yeah, but I'm just saying like this is a kind of contrived case, and like you could come up with a situation in which this 1 is actually very important. Like it's like here. So this is 4, 3, 2, and then like let me try and see if I can make something here. Like let's say this is a 1. This is a 1 to this node, and then like maybe we have like a 5 that points this way. And in reality, okay, so the minimum spanning tree in reality is like cut the 5, right? Delete the 5.
Yeah.
And maybe we'll make this a 6.
Okay.
We can't actually delete that 6 ever. Wait, do I want this
Yeah.
edge? I think I want that edge. So we consider deleting the 6. And we can... Wait, maybe this is an incorrect example.
Another question I have is, when do we run BFS? Like, I think I don't understand the order in which we run BFS and then pruning. Is it just we alternate? We prune and then we run BFS and then we prune?
Yeah,
Not
yeah. So
always.
Right,
we
that's, I
prune,
guess I don't
prune,
follow.
and if prune succeeds, then we run BFS. If the prune fails, then we just discard the bigger half, right? So we just like
Yeah.
forget
Okay, if pruning leaves a valid, I guess how do we know if prune?
Well, we always run BFS immediately after pruning, right? We run pruning and then we do
We wouldn't
BFS
know
to
if it
determine if
succeeds
it's
or
a
fails without.
Yeah. It's just whether like we store the result of the BFS or not, I guess is the key there.
We run BFS to determine if pruning failed.
Yeah.
I see.
And then
Okay, but when you run BFS to determine if pruning failed, how do you do the copying? Like we.
Yeah.
How
That's
do you run?
So we don't store the copy. We don't need a separate copy, right? We just use the copy we had from last time essentially, because like the worst case scenario is that we don't reach any new vertices, but the vertices we've already reached via the previous incremental BFS shouldn't change, right? So like
What if the
we're
worst case? Oh, sorry.
so like so let's say we're recursing into here, we're working here, right? So like anything that we've already reached via like edges from down here shouldn't ever like be disconnected by like stuff we're doing here. Does that make sense?
I think I didn't follow. Can you try saying it again? Sorry.
So like like here, like so let's say we've already added like this 2 edge here, and we're trying to figure out whether we need the 5, 7, 6, or 8, right? Like no matter what we do to the 5, 7, 6, or 8, the vertex reachable by the 2 edge shouldn't ever change. So like in some sense, we've like stored like some result already. So we have like a copy that we can like I don't know, like run our old
I guess
BFS.
what I'm saying is if we use R to run BFS on, let's say, like the first 3 quarters, then R is now like a different thing. It's like 3/4 instead of half. But if we determine that was actually wrong and we don't want the first 3/4, we want like a different thing, then haven't we like messed up our R and so we can't easily go back to it? Because we only have one copy of it?
Okay, so basically, so the R, okay, let me see if this works. So basically, R stores the information in here, right? Like in the lower half.
Okay, sure.
And
And then we want to determine we're like bisecting at the like 3/4 mark or something.
Yeah, so we find the median, split it in half,
Yeah.
then we add this and we run BFS, but we don't touch R. We only use R to query. We don't modify R.
Well, how do we know if our BFS succeeded if we don't modify R?
Via a counter. So if we manage to
sorry. Okay.
Yeah, so if we manage to reach a new unreachable vertex, which is
you count.
Yeah, and then the check of whether the counter equals V is pretty trivial.
Yeah,
so like, oh, new vertex +1. Oh, new vertex +1.
Just like write down the order of the steps that we do or something. It's like you prune.
Yeah. Let me.
I'm just being low, but you prune,
Yeah, let me.
and there's two possible results of pruning. If you find an arborescence and the prune was successful.
Can we taboo the word successful? I don't really like that.
I don't like. Sorry. Yes, there are two possible results of the prune. You find an arborescence, and then you delete the top, the edges above median.
I guess I can say work and fail.
Or you don't find, or no arborescence.
Can we? I like arborescence and no arborescence. I think that's very descriptive.
If prune finds, let me see. I guess you're typing about prune
race.
Find arborescence incremental BFS. Okay, let me see here. Prune to median, yep. Find arborescence. If it does find an arborescence, delete edges. Yes, that's correct. Okay. If it does not find an arborescence, don't delete. Yes. Okay. And then 3, string search space. Yeah. Via recursion. Yeah. Okay.
We run BFS to determine if we find an arborescence.
But there's some tricky thing about that where you don't really run the BFS, because if you really ran it, you would overwrite some information you're using or something, and that's the part
Yeah.
It's 2 different types of BFS, right? So
right. Yes.
So for the case where we don't find an arborescence, then we run an incremental BFS on the lower half, so we can add it to our tree structure, and then and then recurse onto like half of the big half. If we do find an arborescence, then we wait, have I gotten that backward? No. Yeah. Okay. Yeah. So let me just maybe write it out.
I'm copying this into the. Nobody on the recording is going to see our chat, so I'm just going to copy and paste it into the.
Oh yeah, that's a good idea.
Okay.
I think this is now somewhat complete.
Yeah. So basically, okay. We find an arborescence. Let me see here. So we find an arborescence, then we know that we have to recurse in here and delete this. Yeah. And then if we don't find an arborescence, then we have to recurse into here, and then we incremental BFS this. Okay, and then in order to determine that whether we can or cannot delete, and then we run counter-based BFS here.
What is counter-based BFS?
So this
is the thing where we don't modify our data structure, but we
just count how many new vertices we reach, basically.
Which takes time.
And the goal is to see if that count matches the total amount of vertices. If we do, we already have an arborescence.
I unfortunately can't access the Excel draw. Sorry.
Oh, did you get kicked? It said a moment.
What just happened?
It says something about couldn't save to the backend database, which I don't understand.
I just
obviously
clicked.
You're using it fine.
Yeah, I got off. I just clicked off that message and ignored it.
Like out of the box, and it should go away.
Oh, okay, huh? Cool.
Yeah, I think it's just something like that. Something about the paid version saving it for you, but
if we refresh, it's not gonna continue existing or something.
Sorry about that.
No worries.
Anyway,
I updated the thing in Discord. Sorry, I should have.
All good.
Put it in Excalibur to start with, so that it.
No worries.
So yeah, essentially, in order to run counter-based BFS, we're just asking our data structure, instead of maintaining like the 0 and 1 bits for each vertex, it also maintains like some header information about the counter. So like how many ones has it added so far, and that's all we need to run counter-based BFS. So basically BFS on the deleted edges, and we see new edge reach at 1 to the working counter. Then once we finish BFS, we have the counter of newly reachable vertices and the counter of already reachable vertices. We add them up, does this equal V, and that determines whether we have a spanning arborescence or not.
Yeah, that makes sense.
And in order to maintain this counter, it's a logarithmic number of bits in V, right? And so it's an additive factor of log V, which should not affect our linear time.
Well, a counter takes log V space, but we need to know how much time it takes to update. Which is V, right? Because we might need to touch. Well, it depends on the incremental stuff, I guess. Was a bit tricky.
Yeah. So okay. So here's the thing, right? We're deleting edges at every recursion level, right? Potentially. I mean, I guess always, but from either the lower half, the big half. But we're removing edges, right? And so we're always shrinking the set of edges by half. And so the maximum number of vertices we can visit is big O of the edges. It's big O of V always, but it's also big O of the edges. And since we're shrinking the edges, eventually we'll shrink it past V, right? And so if there's only V minus, V over 2.
Yeah.
If there's only V over 2 edges left, then we can't possibly fit all V vertices, right? At most V over 2. And so we start off with potentially more time, but because we're shrinking the edges, eventually it will decrease past V.
I actually have to get to bed, but this is very interesting, and I hope you all.
Yeah,
I hope to see it right up or see the recording soon. But either way, very interesting.
Yeah, I think I'm pretty much done actually. I mean, we've established the rudimentary version with the just backup copy, which hopefully shouldn't be too controversial. And we get E plus V log V, which is equal to Dijkstra time running with Fibonacci heap, which is so complex you would never actually want to implement it in practice. And so we managed to achieve E plus V log V without resorting to the Fibonacci heap. And so our algorithm can actually reasonably be used in some scenario. which is already an improvement. And then with our counter-based BFS and our pruning procedure in these steps here, we remove our need to like recopy at every step, and then which is slightly more sketchy, I guess, but hopefully I should be able to formalize it better with more time to develop it. So yeah, that's essentially the algorithm.
Yeah, I would good night. I would definitely appreciate it if you could just write the algorithm in pseudocode, because I think that would make it a lot easier to follow.
Yeah. I have a pseudo write up, which I will touch up.
Yeah, this is interesting. I'm not convinced of anything, either it being right or it being wrong. I still need to think about this, but yes, this is definitely interesting.
Yeah. Hopefully, like the first step where we do incremental BFS and then having a copy should be much more clear. That's correct. The second half, it's a bit more intricate.
Yeah. I'm gonna try. I contrived this graph here such that we'll land on 5 at the end, and I just want to run through this one once. And 5 being interesting because that means we do like a prune, then a upwards BFS, and then a prune again. Assuming I worked that out right. So 1, 2, 3, 4, 5, 6, 7, 8. So okay, subdivide here. So we're gonna cut out 5, 6, 7, 8. So now what we do here is we are going to run incremental. We're going to run counter-based BFS from this. This is the root, by the way. But that's kind of obvious. So we hit that. We get 1. We hit this. We get 1. We hit this. We get that's 3, 4. So we hit 4. So that's not equal to 5, which is the... What's that?
Yeah.
Yeah, so
just following along. Yeah.
That's not equal to 5, which is the number we need, because 5 is the amount of edges minus the root. Or sorry, the amount of nodes minus the root. So this is not a tree. So we go into step 2b, which means we don't delete them up, and we add the bottom half. So I'm going to go ahead real fast, and I'm just going to I think I'm going to color my lines here and say, we're going to circle things in green that are for sure like in the arborescence.
Yeah.
And I'm going to use red to cross out from now on. Okay, so now we cross out 7 and 8. So we run from the root node, do our BFS, our counter-based BFS one more time. We already know that these 4 are reachable. Were we supposed to be caching these, like the boundary of our BFS search from before?
Yeah, I don't think you strictly need to, but yeah,
like if we
it'll
run
only
counter-based BFS again, we get another. What do we get? No, that's still n log. That's n log n, right? If we just run a full BFS again.
Yeah. I think like since you have access to which edges are in the bigger half, you can just only run it starting from like something that's already reachable.
The known like counter-based BFS reachable set, which is just this node. Wait.
Well, I mean, you're not adding any edges over here, so like we don't really need to consider it. Like when.
Oh, you're just saying we look at the edges that we added.
Yeah, because you have access to them, right?
Okay, so So this one, we can ignore this one because we already knew we could get to it from before.
So so we're trying to add edge 5 and edge 6 in, right?
Right. We want to add 5 and 6 in.
Add 5 in. We're like, okay, is the source reachable? Yeah. So let's maybe start from there. So it's like mark that, I guess, and then
is the source reachable? Yeah, the source of 5 is reachable, and therefore this is now reachable.
Yeah.
So add 1 to our counter. Add 1 to our like, you know, our new counter. Our new counter is 1. And hooray, 5 plus 1 is 6, or 4 plus 1 is 5, which is the number that we wanted to find, right? In theory, you would have to also like inspect this edge as well if you don't immediately find that you've hit the target amount of nodes. But in this case, the first edge we checked, we noticed that that allowed our next node to join. So as a result, we don't get to add these yet, but we do get to discard these.
Yes.
Okay, so now we toss the 6, tentatively toss the 6, and
yeah, we run it starting from this again, and then we count. Okay, this is 1, 4, and then
we run it starting from what again? Like what memorized information are we starting from?
So okay, when we're adding this edge here, right? We just have to look at like the source.
Are we adding it? Is adding it what we're doing? Because like the last iteration, we like deleted these 2 and ran the full algorithm, including the 6.
Maybe add is like a bad word. Like I just say maybe scan is a better word. So like 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 when we're putting this edge into our traversal, right? Like if its source is reachable, we can we can start BFS from here instead of the source, or I guess like from here would be better. But yeah.
But you're assuming that we already somehow know like the information that we're basing this off of has to be.
Yeah, like we've already marked like these guys as reachable, right?
We've marked. Hold on, let me color it. We've marked this vertex, this vertex, this vertex, and this vertex, and this vertex all as reachable.
Yeah.
We did that on the first iteration, not on the second. We've done 2 iterations so far. We marked those as reachable in the first iteration, and that's reachable with the things that are already colored in green. So we now run again, given the information that we gained when we were able to add the edges, not from the information the last time we ran, because we didn't get to add any edges last time.
Okay, so maybe let's backtrack a bit. Okay, so we determined that we can get rid of 7 and 8, right? And we know that these are reachable. So let me just put a
actually I'm going to circle it down here. It's like on iteration 1 we accomplished this.
Yeah.
On iteration 2 we accomplished this.
Yes.
Okay. On iteration 1, on the successful iterations, we get to mark nodes as induced, right? We don't get to mark anything as induced when we cross things out here, right? Yeah. So we now have to start BFS again from the set of green colored nodes, I'm saying we're saving that from iteration 1, and we write to that save because we were successful and we got to circle things in green. Yeah. So then we do our incremental BFS again. We realize the 6 is pointless. We do the 5 and we're like, oh yeah, we got all of our vertices. Then that tells us that we get to, what does that tell us?
Get rid of, wait.
That tells us we get to delete the 6.
Yeah, because we try to get rid of the 6, we do the 5, and then it works. Can get rid of the 6.
Yeah, and then we don't already know that we have to add the 5, do we?
Yeah, we don't know, but
no, we do know. We do know, because if we if the 5 was still up in the air, then that would mean that when we searched these first 4, we would have found a minimum spanning tree or a minimum
So basically,
arborescence.
that's sort of like the final case because the algorithm is always able to pick like the correct half, but if you only have one element, then there's no half to pick from, and so basically it's a special case where you have to argue that okay, if there's only one edge left, then
it always
that
gets
edge, essentially.
It always gets added, right?
Yeah.
That makes sense. This jives in my head. That feels linear.
Yeah. I think I the only thing I need to argue left is like maintaining the counter doesn't grow past linear.
There's only one BFS going on here in what we just did, I think what we just did makes the most sense out of anything anyone's said so far. No offense, but like I think I just needed a good example. So like I think this incremental BFS and the counter-based BFS, I think those are the same thing. Am I
Yeah,
wrong?
yeah. So essentially, I think you simulate the counter for like the degenerate case where there's a cycle, right? I don't think you formed a cycle here, did you?
No, there's no. This is a DAG.
Yeah.
So
yeah. I think
but like I still did use the cycle, like, or the counter rather. Like I used the counter to determine if all the vertices were touched.
Yeah. So yeah, the counter is, I guess, like like because the BFS when we succeed in adding is incremental, we're sort of like removing some work we have to do for like future runs of the counter-based BFS, and so it feels like we're doing the same BFS run, if that makes sense.
Yeah.
The whole point of like incremental BFS is we're trying to remove work from future recursions.
Yeah. Yes. I'm trying to figure out how this would not be linear. Like, what are the steps that are sketchy in here? Like, we are doing this BFS step of like, checking like the 6 and the 5 potentially a couple of times, but that should also geometrically.
Okay, so, yeah, for the 6, like we're going from like reachable to reachable, so like it's useless. We can forget about it.
Well, yeah, but you say that as a human, but like, like.
Yeah, no, but like like the algorithm, when we're trying to like look at it, we're trying to we're sequentially through like every edge in the big half.
Yeah.
We're like 6, going from reachable to reachable.
Sure, but like it doesn't have to be going for, like, I could have written the graph in a different way such that it wasn't. Like, yes. I just mean to say, like, I don't think that changes the analysis. Like in either case, we're running BFS on these two edges multiple times over, and in doing so, I still think the first time we ran it on 7, 8, 6, 5, the second time we ran it on 6 and 5, and it seems like you're always running it on half as many, so you still get BFS running.
Yeah, it's like that's like the whole crux of the thing is you always
hold on, that runs E times, but the difficulty of the BFS that you run is equal to the amount of edges that you're looking at. Is that right?
Yeah, it's upper bounded by the edges, right? Because more specifically, the number of edges connected to the root. Because like if you have like a disconnected component somewhere because you delete the edges, then like you don't have to traverse that.
Yeah.
So, and because the number of edges is always decreasing by half, like at some point you'll like no longer be O of V traversal and just O of edges traversal.
That's clever. I'm like,
Yeah, I mean,
I think I don't see what's wrong with it. Um, huh.
yeah, I mean, like, yeah, it's just two key ideas. All right, like number one, incremental BFS, and number two, pruning, and
Yeah.
those are the only two key modifications to Camerini's algorithm that we need.
Right.
Um, and so I guess I think we've gone on for about like 2 hours ish.
Yeah, two
So
and a half. Yeah. Sorry
yeah, so
if
I
I'm
think this,
taking your time, but like, yeah, that's cool.
yeah, so I think that's a good place to leave it
I
now
think
that we've
so. I think so. That seems to.
yeah. So I guess like one final thing I want like to leave you guys with is that you know, purportedly my algorithm quote unquote beats Gabao and Tarjan's algorithm.
Right.
However, if you will follow the chain of deduction here, so my algorithm is just two key modifications to Camerini's algorithm.
Yeah.
Camerini's algorithm so well because you were able to do binary search on an unsorted list via linear time median finding.
Mm-hmm.
And linear time median finding was discovered in part by Tarjan. So in an ironic / poetic chain of events, we've used Tarjan to beat Tarjan. So
Nice.
yeah, I guess the man won a Turing Award for a reason, right?
Wow. Cool.
All right. Yeah, I guess thanks for watching. Hopefully,
Yeah.
hopefully that was a proof sketch and not a sketchy proof. But you know, there's definitely
Yeah.
more. There's definitely more.
I'm like given like in given the Bayesian prior of just my ability to reason about algorithms, I would rate myself like 80% confident that this is linear time. I have to think about it more. Given the Bayesian evidence that it is like given the prior that this is an unknown like unsolved problem, maybe I'll give it a 60%, but or like a 50%.
Yeah, yeah.
But like this
I think
makes sense.
I think like the E plus V log V result much more concrete.
Yeah.
Like that's barely even any work on my part. That's just incremental BFS.
Right.
Yeah. So I think that should be like, you know, a solid 99% sure on that. The second part, pruning, is slightly more intricate, and it's good to be skeptical about that.
Yeah. Yeah, but I think
So
I
yes,
think it works.
yeah. So we're aiming for O of E, but worst case scenario, we're still improving it to O of E plus V log V, which is equal to Dijkstra. But we achieve E plus V log V without using the Fibonacci heap. Because in practice, using Dijkstra, you would use the binary heap and not the like incredibly complicated Fibonacci heap, right?
Yes.
Yeah. And so Fibonacci, good theoretical object, but like I don't think anyone actually uses it in practice.
Yeah.
Like I think the concept like literally astronomical or something.
I'm pretty sure like I'm pretty sure if you implement that, just the overhead is going to nullify any performance gains you get for any reasonable data set.
Yeah. So and my algorithm, the worst part of it is the linear time median finding. And if you're willing to sacrifice like guaranteed linear time or like linear time with high probability, you can just replace it with quick select or something and get pretty good performance.
What's quick select?
Oh, quick select is randomized median finding, or I guess randomized orders.
Oh yeah, okay,
Question.
yeah. And you're saying, what are you saying? Does that, if you have that, then what's the result?
So basically, so I think like linear time median finding runs in time with constant factor like 20-ish something times E, or I guess times N. If you move it to quick select, then it runs in expected time like 2 or 3N. But the variance can be a bit more because it's in a randomized algorithm, so you don't have like a guaranteed upper bound.
Yeah, but like so okay, so in worst case you would end up with something
so
that's
quick
not
select is just
linear.
quick select is just like one half of quicksort, and so basically you get with high probability linear time, but worst case it might degenerate to quadratic time if you're not careful.
I see. Yeah, that makes sense.
Yeah, and essentially, so basically, I guess like the like almost guaranteed result is that we've come up with a practical E plus V log V algorithm, and then the slightly more intricate goal is that we come up with an O of E algorithm.
Mm-hmm.
But yeah.
Yes.
So I guess thanks everyone for watching.
Thank you.
Everything makes sense.
Yeah, that's very cool. I appreciate the talk.
Right. Yeah. I guess like let me know when you've ended the